In this lecture, I'm going to talk about fuel cells, a source of power for the future. It's already existing in some parts of the world, giving power and being used in the automobiles and some of the inland water transport ferries, etc. This is again something similar to your batteries, but operating in a different condition. One of the requirements to which shipping is proceeding is for a zero emission. Present day system, we have auxiliary engines operated by the diesel fuel to run as a prime mover for the alternators. So emission is there, they want to make a zero emission, so they are looking for the alternatives. Even for the fuel, they go for hydrogen or ammonia, something which will not produce too much of emission and they can keep the greenhouse gases under control. One of the possible power sources is that the fuel cells, lithium ion batteries, solar energy, and development is progressing through using wind energy to develop electrical power. As one of the power sources, we will consider the fuel cells today. The fuel cells operate by making the hydrogen to react with oxygen. For example, any cell or any battery what you take, the output is DC, and the fuel cell output is also DC. The voltage here ranging from somewhere 0.6 volt per cell to 1.23 volts per cell, depending upon the manufacturing. You know very well, lead acid battery, it is 2 volts per cell. Nickel cadmium cell, it is 1.2 volts per cell. Lithium battery creates 3.1 volts per cell. Similar way, fuel cells, of course, it's ranging here. The question of reaction of hydrogen with oxygen. So here again, we are using anodes and cathodes and possible electrolytes. But in fuel cell, we normally use a membrane electrolyte which allows hydrogen ions to pass through it. The hydrogen ions combine with oxygen on the other side to produce the power. The outlet is always or output is always a water vapor. There are different types of fuel cells manufactured. They have been all tried out, all successful. But most commonly used fuel cell at the moment is Proton Exchange Membrane fuel cell. Proton exchange, that means the hydrogen atom, it is ionized. Hydrogen atom has got one electron in its outermost orbit. That one electron is removed and hydrogen becomes hydrogen ion. Once the electron is removed, remaining is only protons. So that's why it's called as a proton exchange membrane fuel cell. And different types of fuel cells already available are there in the market. So a fuel cell combines hydrogen and oxygen to produce water, heat, and electricity. Normal operating temperature slightly above 100 degrees centigrade. This type of proton exchange membrane fuel cells. So the different types of fuel cells are alkaline fuel cell, phosphoric acid fuel cell, polymer electrolytic membrane fuel cell. They are slightly different from the proton exchange membrane fuel cell. We got solid polymer fuel cell, molten carbonate fuel cell, solid oxide fuel cell, direct methanol fuel cell. Methanol is used as a dual fuel in the diesel engines to control the emissions. Microbial fuel cell is nothing but biofuel cell. It is also under manufacturing in so many eastern countries. But here in this lecture, I am going to concentrate on what is called a proton exchange membrane fuel cell. The basic operation is hydrogen to react with oxygen and the power is produced. This is a sort of a sketch given. So on the anode side, I send that hydrogen in the form of a liquid or generally it is sent in the form of a liquid or gas. Now normally they say hydrogen gas. At the anode, the hydrogen splits into hydrogen ion and electron, and then electron is released to carry the current from anode. On the other side, cathode, you are sending oxygen. So this electron goes to the cathode. Meanwhile, the hydrogen ion passing through the membrane, you see hydrogen ion passing through the membrane, it reacts with oxygen here and the electricity is produced. The electron which is carried in the outer side, it is given to the load, electrical load, maybe a bulb or maybe anything, whatever the load you want to connect, and it comes back to the cathode to join with the oxygen. The outlet is always water, some sort of a water vapor which can be condensed and collected into the tank, but it is not palatable. It can be reused. The collected water can be electrolyzed and hydrogen can be released for the continuous operation of the fuel cell. The present day system slightly differing because ABB is suggesting some other good alternative that we will see later. So this hydrogen atom contains one free electron in the outermost orbit. The nucleus contains mainly protons. This electron can be dislodged by means of a catalytic process. So the anode where I am going to send this hydrogen should have a catalyst to break this hydrogen into hydrogen ion as well as electron. Normally we use platinum catalyst and the anode general preferred material is graphite, and it is added with this platinum catalyst to ensure that the hydrogen coming in is split into hydrogen ion and electron. Electron will travel outwards in the circuit to carry the current because electrons are all charged carriers. This is for the explanatory purposes. It is taken out from Wikipedia only. Just for explanatory purpose, I am using this particular thing. You see the pink color inside, that's a membrane electrolyte. I will come back to the material of the membrane electrolyte. It is something transparent one which is allowing the hydrogen ions to pass. It won't allow anything else except the hydrogen ions to pass. You see the picture looks a little bigger, but in fact the fuel cell after assembling it is a very small one. All these anodes etc. they are all in terms of micrometer sizes or millimeter size. So it is not very large. It's quite compact and it can be used. You see the blue color here. There are two things adjacent to the membrane electrolyte. One is the anode, another is a cathode. This can be put in any side, either right side or left side or this side or that side. It is not immaterial because they are similar. And only thing is that catalyst added is slightly different, so that we have to be careful. Where I have got the platinum catalyst that is used as an anode, on the other side of the membrane where I am going to send the oxygen, I use nickel as a catalyst. Again, the gas etc., hydrogen, whatever you want to send it here, it has to be properly channeled. So there are something called what they call flow fields. Some sort of a grooving or that guiding arrangement is given. They call gas distribution channels, or they say flow fields. These gas distribution channels are created in that anode itself. It's not a separate one, even though in the picture now they are showing separate for explanatory purposes. That gas distribution channel is very well engraved into this anode or in the cathode. Both sides will have that gas distribution channel. So one side I am sending hydrogen marked in that yellow color. Here, that blue color is converted into hydrogen ion. The electrons escape externally. You got a collector plate. And hydrogen ions pass through this membrane. And here the oxygen is coming. You see that oxygen is allowed to come, the blue color. The outlet is always water. So it's not non-dangerous. Actually, this thing, hydrogen, apart from this fuel cell application, they are using it for gas building also. Instead of oxyacetylene, they have already developed oxy-hydrogen gas. So the hydrogen has got as a is acting as a fuel to give energy. You see this conceptual part of it. You see here this blue color and this thing what's shown here. It's a membrane, and you got these plates adjacent anode, cathode, and once the electrons are released, it has to be taken. So there will be a metallic plate to carry the current, what they call bipolar plates, and it is going to the external sector. So on one side, you got a terminal, like a normal battery, you got a positive lead as well as negative lead. This also will have the bipolar plates on one on the positive side and one on the negative side. Normally, we say that anode is a positive and the cathode is a negative. So you have got this bipolar plates on both sides of the fuel cell. You see this membrane. The material used is called perfluorosulfonic acid ionomer. Perfluorosulfonic acid ionomer. This is the membrane material. You see this is a rolled sheet. The thickness is somewhere around 500 micrometers or something like that. Very, very thin one. That's what used as a membrane electrolyte. You see, this is a normal battery what we are using on board the ship, like an emergency battery or wherever we are using for some power station general arrangement. Same way the fuel cells are also arranged. This is not a fuel cell. This is a lead acid battery just to show how they are arranged. For example, if you want to develop 24 volts emergency battery by using lead acid cells, what is commonly available on board the ship, each lead acid cell can generate 2 volts per cell. So to obtain 24 volts, I must use 12 groups of lead acid cell only to generate 24 volts. But 24 volt is not sufficient. It has to deliver something called a current. Normally, we rate the batteries in terms of ampere hours. So much of amperes per 10 hours. For example, if your battery 1000 ampere hour rated, it delivers 100 amperes per 10 hours. So that 100 ampere each group has to provide. You see here, these are all the different groups what you are finding here. Each group internally you will have anodes and cathodes, what we call a combination of cell. Electrolyte is a liquid electrolyte. You know that in lead acid battery it is a diluted sulfuric acid. So the anodes and cathodes are dipped into that diluted acid. And if you see here externally, this is a positive terminal and the red color is the negative terminal. This group is connected in series to the other group externally. Same thing here, it is externally, it is connected in series to obtain the 24 volts. Each cell, the voltage across these two terminals is only 2 volts. They are connected in series externally to get the 24 volts. But internally, same way you got anodes and cathodes, maybe 60, 70 or 80. They are all connected in parallel. Inside the group, they are connected in parallel to augment for the current carrying capacity. If I want to improve the ampere hour capacity, voltage can be same. Only thing I want to improve the ampere hour capacity. If I have enough space, I can add more number of cells internally. More number of cells means more anodes and cathodes. Because these things, they share the current because they are connected in parallel internally. In parallel circuit, current is divided. So they share the current for delivering the required current to the external load. So externally, they are connected in series to build up the voltage. Internally, the cells are connected in parallel to cater for the amperes requirement. Same way in the fuel cell also. This arrangement inside connected in parallel, we say stacking. The cells are getting stacked to provide the required current. The voltage is obtained by means of connecting them externally in series. Now you see here, the one of the arrangement called stacking. This is one particular cell. The yellow color is a membrane electrolyte, and you see that pink color adjacent to that, they are the anodes and cathodes. At the end, you can have the collector plate. Both sides you can have collector plate, which can be connected into the external circuit. There will be end cover, etc. So this is called one stack of the fuel cell. Now, if you count it here, you got 1, 2, 3, 4, 5, 6, 7, and 8. 8 cells are stacked together. The current is shared by the 8 cells. By chance, it is giving, each group is giving 16 ampere current, for example. So each cell will share 2 ampere current. Accordingly, the construction size, etc., they start with it. See, this is arrangement for a fuel cell, a completely stacked fuel cell. You see here the bottom, this is the thickness of the fuel cell. That's all. Not as large as you saw in the previous figure, such a big arrangement. No, it's very, very compact. This may contain about, say, 50 or 60 fuel cells. They are all in parallel. And you see here, this is the two terminals here, the gray color. They are the two terminals. The output voltage, depending upon the manufacturer, depending upon the thickness, depending upon the amount of gas handled, it can vary from 0.6 volt to 1.23 volts. Suppose I want to build up, let us say, 110 volts or 120 volts. Each group is going to give only 1.23. So I must have 100 groups like this. And they are connected externally in series between these electrodes. Positive, this is positive terminal, negative terminal. This negative terminal will be given to the positive of the next. So I must arrange something like what you saw in the previous picture. We'll arrange a group like this. All these things can be stored in a container or whatever the arrangement is there that goes different from manufacturer to manufacturer. Ultimately, I am getting so much of volts and required current. ABB, because this is little cumbersome and still it is there. This type of arrangement is always there. And they are transported in terms of a container. So your bunkering requirement will be only existing container can be disconnected, brought onto the deck, and that charged container can be taken onto the ship. It can be replaced. Normally, we don't have a facility for recharging on board the ship, where they are using this type of cells. So ABB has come out with an alternative. And even some of the ships which are using lithium ion battery, off late, a coastal tanker has been launched by Japanese firm. Complete arrangement is only lithium ion battery. So they are taking extra containers, etc., wherein they have to store and then as a standby. If one is fully utilized, the other one can be replaced tentatively. The discharge one can be sent ashore for charging, or the charged container is available that can be replaced on board. So there is nothing called a pollution effect regarding the bunkering arrangement. There is no need for any extra sampling or anything. As long as it is assured that it remains charged, it may come for whatever time they are specified. Normally, I don't, except in the automobiles, I don't think it is being classified for so much of kilometers because out at sea, we can't exactly predict the distance due to the sea conditions, underwater current, and other storm effects or cyclonic effects. The ships may get drifted. So, exactly, we can't say after 200 kilometers you charge the battery, etc. But in shore, it is possible. So all the electrical vehicles on in shore they say that after so much of kilometers you can charge it. But here they go by hours. They come for so many hours. Of course, there are indications when that fuel cell or something is going down, when the voltage is slightly start dropping. You change out the standby one and then remove this. Arrival next port, you can have the charged one given. So ABB is suggesting this particular thing. It is a small. They say why not we have a bunker tanks on board the ship, hydrogen bunker tanks. Is only in animation. ABB is suggesting this. The blue color is hydrogen tanks. You can bunker it. Take the oxygen from the atmosphere. So as long as you have got enough bunkers, the fuel cells can operate 24 by 7 or 24 by 7 by 360. So outlet is full water. The water can be collected and stored. But only thing it's not palatable. Remaining, if you want, you can leave it as a vapor. You can go to atmosphere. Same thing. The fuel cells. You got a membrane electrolyte. You got this anode and cathode. At the anode, that ions are hydrogen is built hydrogen ion. Electrons are liberated, yellow color. It comes back to the cathode. This is done by ABB. Suggestion, but maybe in the future it may become a reality also. And this is what they are trying to achieve. What is called regenerative fuel cell system. Daytime, they can get the electrical energy from solar cells, or when there is full of cloud, or when there is no sunlight available, you can go for the fuel cells, which is shown at the bottom. The outlet is water. Water is collected into the water tank. This water can be electrolyzed, and again that hydrogen can be supplied to the fuels for a continuous process. Again, it all depends upon the amount of water collected, amount of power consumed, amount of power produced. You can't make a hard and fast rule. This should come for so much, etc. But it's a idea. So accordingly, the capacity, etc., has to be modified while manufacturing. Is there any type of battery, and we are supposed to operate these things within the permitted limits? For example, even household battery, when you are having inverter, they say ampere hour, you ensure that the load connected meets the requirement of so much of amperes per turnover. For example, if it is 180 ampere hours in your household battery, it is supposed to deliver 18 ampere per turnover. The battery has to be healthy. If you use it more, the battery will die very fast. Accordingly, as an engineer, you can calculate the power that can be connected to these batteries plus 12-volt battery in household, 18 into 12, 216 watts, 216 watts. That's all you can connect. For example, your LED bulb may consume about 9 watts or 10 watts. Your latest fan, inverter fan, consumes about 35 watts. Your laptop, computer, etc., they may consume about 90 to 95 watts. You calculate what can be connected when the main power is off and inverter is on, so that the battery can supply you for next 10 hours without any problem. And battery also can be very healthy. But this is the arrangement what they are doing. Instead of having a normal battery, they are going to do with the fuels. But fuel cell, if you want to operate it continuously, you must have a continuous supply of hydrogen. As we saw in the very beginning, the different types of fuel cells. For example, if you take a methanol fuel cell, already it is under developed. Commercial models have been developed. Methanol, hydrogen can be released by a process called a reforming process, or by a steam injection process. Hydrogen can be released. That hydrogen is going to react with the oxygen. Ultimate principle is hydrogen reacting with oxygen. And all safety precautions should be observed because we are going to use hydrogen. and people are having some illusion or fact. I'm sorry to say this particular word, but hydrogen means it will explode. No. Hydrogen as a gas, it has to come within that LFL and EFL, 4% by volume, 74% by volume. Oxygen should be minimum 11% by volume. And third thing, hydrogen should reach a temperature of 560, that is the auto-ignition temperature. So without that, hydrogen cannot burn unless I have an ignition source or I don't. If a situation says that the temperature can go beyond 560, so hydrogen will not burn. So that particular thing we can remember. So it's not very dangerous, but we have to take all the precautions. Hydrogen is has to be stored in a cryogenic temperature. Of course, all these constructional aspects of the fuel tanks, etc., are given IGF code. With this, I hope I have made a small, clear picture regarding how the fuel cell is constructed, how the fuel cell is operating. Thank you very much for the patient listening.